Imagine staring at the James Webb Space Telescope's latest deep field image. A forest of faint galaxies, frozen light from billions of years ago, drifts across your screen. Colors you can't quite name. Structures too small to see, but somehow you feel their weight. Then you notice one chilling detail. A galaxy is moving as if something is missing. The invisible scaffolding that should be holding it together isn't there. And the laws of physics begin to slip. Tonight, we're descending into 7 unsettling clues from JWST that some galaxies may exist with little or no dark matter at all. Objects that, by our current understanding, simply shouldn't exist. Number 1 is the one that doesn't just bend the rules of cosmology. It snaps them. I've spent months going through the papers, the spectra, the quiet arguments buried in the footnotes. What follows may change how you think about what is really holding the universe together. Let's begin. Number 7. The galaxy that started a fight in 2018. Peter Van Dockum and his team at Yale announced something outrageous in Nature. The ultra-diffuse galaxy NGC 1052 appeared to have almost no dark matter. They measured the motions of star clusters orbiting inside it, and found them moving as slowly as if only the visible stars were there. To scale this, imagine weighing a city by tracking the speed of its cars, and finding only enough mass for the cars themselves, no buildings, no ground. If DF2 is real as advertised, then dark matter is not a universal cosmic glue. It can be turned off, or stripped away, and that means our neat picture of galaxy formation suddenly has exceptions. We have not proved DF2 is truly dark matter free. We have also not proved that galaxies like it cannot exist. Number 6. A twin that made it worse 1 year later, in 2019, the same team reported another ghostly system in the NGC 1052 group. NGC 1052 DF4. Again with dynamical measurements suggesting a severe dark matter deficit. Published in the Astrophysical Journal Letters, it wasn't just a fluke, now there were 2. On Earth, it's like discovering not 1, but 2 skyscrapers standing without foundations, side by side in the same city block. Theorists raced to explain it. Maybe these galaxies had their dark matter torn away by tidal interactions with a larger neighbor. Maybe the distance was mismeasured. Maybe the data were biased towards slow-moving tracers. But if even a fraction of these explanations fail, then nature has ways of building large, fragile galaxies almost entirely from ordinary matter. We have not settled the argument. We have also not settled whether DF2 and DF4 are warnings that our models are too simple. Number 5. Webb looks back further in time in 2023. JWST's early release science programs, including CEERS and GLASS, began resolving compact galaxies less than a billion years after the Big Bang. Papers led by researchers like Swara Ravindranath and Adriano Fontana used Webb's exquisite infrared spectra to estimate their stellar masses and sizes. To picture these, think of a Milky Way's worth of stars crushed into a fraction of its radius, like fitting an entire continent into a single city. When astronomers compared the inferred masses to the way some of these systems bend light and cluster with neighbors, hints emerged that a few might be more dominated by normal matter than expected, at times approaching the threshold where dark matter's grip looks suspiciously weak. We have not yet cleanly measured a dark matter-free galaxy in the early universe. We have also not confirmed that every early galaxy follows the dark matter blueprint. Number 4. Rotation curves that don't add up. The idea that galaxies might exist with little dark matter did not start with Webb. In the 1970s, Vera Rubin's careful measurements of spiral galaxy rotation curves showed stars orbiting far too fast for visible matter alone. That was one of dark matter's birth certificates. Rubin's galaxies are to us what highways at night are to a pilot. Ribbons of motion revealing the underlying mass. Now, with JWST, teams such as the KMOS-3D and TNG-50 follow-ups are mapping rotation curves of very distant galaxies using rest frame optical lines redshifted into the infrared. Some high redshift disks appear surprisingly kinematically hot, with motions that can be fit either by massive dark halos, or by modified gravity-like behaviors in dense regimes. We have not abandoned dark matter. We have also not conclusively ruled out that gravity itself may behave differently on galactic scales. But what's coming at number 3 pushes beyond rotation, into the fabric of structure itself. Number 3. The missing scaffolding problem. In 2022 and 2023, Webb deep surveys like JWST revealed surprisingly massive, compact galaxies when the universe was only a few 100 million years old. Teams led by Ivo Labe and others reported candidates with stellar masses comparable to the Milky Way at redshifts above 7. On human terms, it's like finding fully formed adult cities in an archaeological layer where you expected only scattered camps. In standard cosmology, dark matter halos grow first, then gas falls in and forms stars. The halos are the scaffolding. But these early giants seem to have built their stellar structures before the scaffolding had time to fully assemble. We have not shown that dark matter was absent from these halos. We have also not shown how our current simulations can easily grow them so quickly with dark matter alone. Number 2. Galaxies that break the relation. For decades, observers have mapped a tight correlation between a galaxy's visible mass and how fast its stars move. A pattern called the Tully-Fisher relation, and its generalized form, the radial acceleration relation. In 2016, Stacy McGaugh and colleagues showed just how eerily tight that relation is. Imagine weighing cars by their engine roar alone and finding a law so precise it works for almost every vehicle ever built. With JWST, we can now extend these tests to much earlier epochs. First results suggest that some galaxies, both compact and diffuse, may fall off the expected trend, hinting at systems where visible matter alone seems to set the dynamics, with dark matter receding into the background, or vanishing from the equations altogether. We have not proven a new law of gravity. We have also not proven that dark matter can explain this uncanny regularity all by itself. Number 1. The galaxy that defies its own shadow. In 2023 and 2024, analyses of JWST data targeting the NGC 1052 group revisited the DF2 and DF4 controversy with deeper imaging and refined distance estimates. Van Dokkum's team and independent groups used Hubble, Webb, and ground-based spectroscopy from instruments like Keck, DEIMOS to pin down individual red giant stars and globular clusters. The result? Even under more conservative assumptions, these galaxies remain bizarrely deficient in dark matter compared with their peers. Their stars, their clusters, the faint glow of their outskirts, all move as if the invisible halo that should envelop them is a ghost of a ghost. If confirmed, they would be cosmic negative photographs, galaxies whose very lack of dark matter becomes the signal, forcing us to admit that whatever dark matter is, it can be rearranged, erased, or perhaps mimicked by a deeper law of gravity we do not yet understand. Now that you've seen them, you are among the few who know that even darkness in the universe can be missing. If some galaxies truly lack dark matter, then our cosmic map is incomplete in a way we never anticipated. This is just one fracture in the standard picture. The next episode dives into how JWST's earliest galaxies threatened to rewrite the timeline of the Big Bang itself, and it's the one that rattled our research team the most. If you don't subscribe, you'll miss that step in the story, and the universe will quietly remain smaller than it really is. Which of these 7 clues unsettles you the most, especially if we confirm it tomorrow?